Yeah, if you make it later, I join more often live. For sure.
Okay, let's make a start. So yeah, good morning or good afternoon, as the case may be, to everyone, and welcome to our seminar this week. So I'm happy to introduce Jens again. I mean, he has been here before, at least once, if not twice, despite the fact that he's quite far away. But by the wonders of technology, he is able to get up before 6 in the morning to give a talk here. So yes, we've heard about functional graph programs before, I think, in some form or other. So this is probably an update and some on some new developments. So Jens is a professor in University of Victoria, and yeah, he's been working on this for some time now. So I remember the first talks in this general direction, at least probably from 2 or 3 years ago. So I'm curious to see how this evolves. So please, Jens, take it away.
All right, now I found the unmute button. Thank you, Raiko. Thank you for inviting me and inviting me back. I presented once before, actually, at this seminar series. Yeah, this is the first time that I talk about functional programming at this seminar series. So I talked about Grape and GrapePress before,
Yeah,
but I believe
may have been
not.
ICGT, maybe.
Yeah, it may have been ICGT. Yeah, absolutely. So I'm just putting this into context of the earlier seminar presentation. There, an earlier version of what I'm talking about here was discussed, but it didn't have the functional programming style yet. So today here, so I'm going to talk about some of the work that was published at ICGT and at the GCM workshop. And this is also a two-part presentation, because last time I was here, I was actually asked, could I give a live demo, and I didn't really do that. I was also early in the morning, and I felt safer with just the slides, right? So here we're trying to do that now. So I'm switching to give a little bit of a live demo of the tool in the second part of the presentation. Okay, so let's see if the slides actually do advance here for my presentation here. So this is the rough outline of my presentation. I'm going to talk about the motivation, why functional programming, why I'm interested in this. I'll introduce graphs and transformations. There's nothing really surprising here for this audience, probably, but I'll maybe a couple of points about this. And then the title of the presentation talks about foundation application. So that foundation piece here is the graph transformation control algebra, which is an algebra that ultimately maybe somewhat akin to the relational algebra for relational databases, defines the formal semantics for those functional programming languages that I'll talk about then later on in this GrapeVine tool, which implements this style of programming. And then I'll talk about that implementation in terms of a tool called GrapeVine. That's the current name of the tool after all of these grape-themed tool names like Grape and GrapePress. We're now at GrapeVine, but they all work together. I'll talk about that, and I'll give the demo. So that's the outline here. And let's dive in. So when it comes to programming with graph transformations, graph programs ultimately define a relation on graphs. Right? So we have a graph program that relates a set of input graphs to a set of valid output graphs. Graph programs usually have a choice of different control structures there. And Raiko and Gabi in their book chapter here quoted at the bottom talk about some common ones, like this choice of different rules, looping constructs, like as long as possible, ALAP. Atomic construct has an atomic block of statements that are executed all or nothing, conditionals, etc. Now, with the practice of graph programming, I find that the implementations often are not really following this relational theory paradigm. Programs are often implemented non-deterministically. So you have non-deterministic choices between alternative rules that may be applicable, or not non-deterministic choices between alternative matches, and some concrete tools of graph programs, they may or may not support backtracking. And also these concrete implementations usually treat the graph, so mind the emphasis on this slide here, the graph is implemented as a singleton. So it's modified in place, and for the program, ultimately a global variable that's mutated while the program executes. So there are some tools that support backtracking. Some of them are still around. Progress is well kind of archived and around, but really no longer available, and really just more there for archival purposes. Detlef's tool here, GP2, is an experimental graph programming language that supports backtracking, and backtracking can also be switched off. So in an earlier version of Grape, the earlier papers, ICDG paper 2017, so describes Grape as a graph programming language that supports backtracking. Grape is a domain-specific language integrated in a general-purpose programming language. And what we've always done in this work is we are looking for bringing graph programming into the mainstream, into software development. So we want to integrate graph programs together with regular programs to solve actual regular problems in software engineering. We've done that, or I've done that in way back in the past as well with other tools, trying to do that, for example, with Progress, and it required quite some integrative and creative hacking to do that, but it was possible to execute those graph programs in Progress with other software, C, C++ components. Grape makes that very easy. That's the philosophy, because it is integrated in the normal GPL, general purpose programming language. And there are these tools that do not support backtracking. They essentially produce a non-deterministic result of an output graph for a particular input graph. AGG makes a random choice between alternative rule applications and matches. It does support conflicting pair analysis to avoid these non-deterministic choices. For Java, there is Grate and Groove. They all have their various niches and particular applications. So Groove for example, for model checking and verification, and Grate for model transformations. So my experience in general from these actual implementations is that if you implement a mechanism like backtracking that allows you to ultimately reconstruct previous graph states to explore other possible graph states, these mechanisms are quite complex and difficult, and the graph programs are fairly hard to to analyze with the stateful computational model. So the drawbacks of this stateful programming model, where you have just one global variable, the graph as a singleton, is that you need to reconstruct the graph state upon backtracking and upon transaction rollback. And in general, that is the same for any stateful side effectful programming when compared to functional programming, is that these programs are harder to analyze and test. So specifically when it comes to Grape and GrapePress, what we've done, and some of you who may have seen this presentation earlier that I gave last time around in this seminar, I talked about this computational notebook that is optional when you use Grape or GrapePress. We use that a lot for applications. So it's similar to a Jupyter notebook where we, in particular in the area of life science and medical informatics, we just use Grape to explore problems that somehow deal with graphs. So here's a little screenshot from a computational notebook. I'm actually switching over to this GitHub project. You can look at this. This is a project where we, for example, transform prescriptions, medical prescriptions, into graph structures. I can put that link later on to Nick to put that if you want to explore that in the on the website here. Yeah, then you can see the computation notebook sheet here. This is how this computation notebook looks like. It has, like other computational notebooks, graphical parts or static parts. This is the graph meta model for this prescription model. It's not so important to understand now completely that meta model, but the idea here was we want to take medical prescriptions, parse them in from a natural language, compute a graph structure, and then find out by means of graph algorithms whether multiple prescriptions are in temporal conflict, so that the patient is maybe unsafe because some drug medications are taken too close together or too far apart, or not together with a meal or something like that. It's not so important. What is important here is just we do many of these applications, and when you have a stateful programming model where you're essentially treating the graph as a singleton global variable, then we found that it's really problematic, because ideally in this computational notebook, you want to have these code cells executed so that they're idempotent. So I can execute them, I can see the result, I can execute them again or make some changes and see the result again. And I don't care really about which order I execute them. It's a functional programming model where you have an input and an output, allows you to have an idempotent execution of these cells. If you don't have that, if you have a graph as a side effectful computation, and it is a kind of a singleton global variable, you have to execute all of these cells in order. You have to, before you execute them again, you have to delete the entire graph state or reset it somehow to a beginning state again, and then you have to go in the same order again, and that really is problematic, and it destroys a good way of exploratively going through that worksheet. So you see, I would have liked to have these code cells here incrementally executed, but at the end, this is a sheet that still uses the old stateful programming model of Grape. At the very end, this is the only computation that happens is as here, you have this clear, which essentially this clear statement deletes the entire graph state again and then executes everything again. So this is the main program. This is not what I really would like to do, but that's what the old stateful programming model forces me to do. So that's so much as a motivation, I guess, why we explore this functional programming model, where we'd really like to have a graph program that takes an input and produces an output, and graphs become first order entities in the programming model. It's not a side effectful global variable. Okay, so functional graph rewriting, graphs are becoming immutable, like in functional programming. They ultimately, once they're created, they never change. They become explicit I/O parameters of graph programs. We have deterministic operators, which of course then now means that a graph program for a particular input graph creates a set of graphs, right? Because it still has this non-deterministic computation of graphs, but now we're creating, ultimately we're computing sets of graphs. We also have, as a result of using this functional graph programming style, a fairly simple notion of ACID transactions, where this is based on this notion of graph processes here, where we can essentially just forget explorations of graph processes that we don't want, that are unsuccessful. And this has been implemented in this tool, GrapeVine, which I'm going to demonstrate here at the second part of this presentation. So some preliminaries here, graph transformations. There's nothing really so surprising here for this group. So we have graphs as nodes, edges, and source and target functions, and we have rules. We have transformations that ultimately are a pair of graph morphisms. So I think that should be well known to this group here. One thing that I want to point out is that we're not, at least in our tool, in our model, we don't have typed graphs, but we have constrained graphs. So our graphs are not constrained by a type graph, but you can have arbitrary graph constraints attached to a graph that enforce some has some similar functionality than if you have a typed graph. So these constraints that we support are ultimately based on this notion of the paper here, a logic of graph constraints. And then our notion of a programmed graph transformation system is ultimately a three-tuple, where we have a set of rules, a set of constraints, and then a set of graph programs. Okay, so then looking at the algebra that defines the formal semantics for our graph programs, this is what's called here the graph transformation control algebra. There's a GCM 2022 paper that talks about this as well, which I think it's a reference that we have or we will be put on the website for this seminar here. It's a single sorted algebra that works on a data type called the grape, right? So again, I like to use that name very often. In this case, the grape stands for graph set enumeration, where which is defined as a finite sequence of sets of graphs. And we have 10 GTA operators with that signature mapping grapes to grapes. So here are these operators on grapes. We have an operator to constrain or unconstrain a grape. So essentially attaching constraints or removing constraints from the grape. We have an operator derive, which ultimately applies a rule to a grape. We have an operator select, which selects a number n of graphs from the last element of a grape according to some total order. We have operators for sequential and alternative compositions of GTA expressions, with a looping operator, which is similar to the as long as possible operator. Also have a search operator, which is a looping operator that searches for graphs that comply with a given constraint, with a given condition. And finally, we have a cut operator, which forgets the history of a grape sequence, and a distinct operator which filters out graphs that are identical up to isomorphism. The GCM paper and these slides here define the semantics of these operators. I think what I would like to do is to keep that for questions rather than going through these slides in detail, and rather actually then move more into the demonstration here. I think I already, when I talked about the syntax slide, I mentioned what these GTA operators are doing, so I won't really go in the detailed definitions of the semantic definition here, but I can keep that when there are questions. So I'll just move forward here. Let's just see what am I doing here for the time. Yeah, 22 minutes in. Okay. So just before we go to the tool, some properties and rationale for these operators. So they are computationally complete, but not minimal. There are a few operators such as constrain and unconstrain that help limit the exploration of graph programs. And the select operator is also included to limit exploration by allowing a heuristic search for a solution of executing graph programs. And the distinct operator is there to avoid state collisions during the solution exploration, sort of to filter out these identical graphs. Okay, so looking at the implementation within GrapeVine here, so the GrapeVine tool is a major revision of these ancestor tools, Grape and GrapePress. So it's really changing the computation model completely to this functional model. GrapePress is this moniker for the computational notebook UI, which is still there. Grape, or this tool, does not require the use of that computational notebook UI. You can actually use just Grape just for developing graph programs just with a normal IDE. So I just switch quickly to the IDE, so it's Visual Studio code, right? And what you will be seeing in the demo using GrapePress and the computational notebook, you can you could just program just as well without the computation notebook within a normal IDE. And underneath, I'm not emphasizing that so much in this talk here. Underneath, graphs are stored in a fully persistent data structure within a graph database called Neo4j, which many of you will be familiar with as well. Okay, so here's a very busy slide that maps some of these concrete syntax statements within Grape to the GTA operators. I don't want to spend too much time on this slide as well, because I think it's better to actually look at some example interactions with the tool. But that's just here for completeness. So I will switch to a view, a browser view of that computational notebook. So when you install, if you want to try out, if you install GrapeVine, it's very easy. I think I made it very easy. It is just a single Docker command, and it just fires up, and you can then fire up your browser and interact with it. You get also the GrapeVine tutorial as a worksheet in the computational notebook. And so what I thought for today, we'll just look at that tutorial and interact with the system with this tutorial. So I hope that's big enough. I zoomed up so that people can see what I'm doing here. So this is the computational notebook. It's similar to, if you're familiar with the Jupyter notebook, has these static elements and also code elements. So here we can compute 2 plus 3, right? So we have 5. It's just a closure command. Maybe we'll start here. So a new grape just gets a new grape, which and the output just has a unique ID of one graph. So this set of graphs here just has one graph and has just a textual ID. If we want to actually see the graph, we can visualize it like this. It's just an empty graph. So here is maybe a bit too much zoomed in because it's more hard to see. Here's the way. Maybe it's fine. This is the way how we can define textually the rules of a graph transformation system. So here, this is the textual input. The tool has this textual input because it is ultimately a domain-specific language within Clojure. But the rules are actually visualized then graphically, so you can actually see them as part of the notebook. Maybe I'll zoom out a little bit because it looks like it's very, very big here. So we have a rule hello, a rule world, and a rule vine, and that's the typical notation where green is something that's created. It's this condensed notation here. So the rule world looks for an existing node, hello, and creates world and a 2-edge. Here we have rule vine that deletes some structure and creates some new structure here. So we can not sure if I we have here a code segment that creates an empty graph, calls it G0, and applies rule hello here, and we can view this, and the computational notebook has a node there, right? But what is significant, let me just demonstrate this here. G0 hasn't changed, right? The G0 is still the empty graph, right? We just have a new graph here, so it's really a you can have as many graphs as you want, and they're immutable, right? G0 is this empty graph that we created, and the application of the hello rule to G0 creates a new graph. So these rule applications can be functionally nested in a nested way of closure functional applications. So here we apply hello on the empty graph and a world, and see the result here. Or we could, and this becomes, of course, at some point in time quite cumbersome with the many brackets here in closure, or we can use closure threading macros. This is the way how you would normally write these programs, right? So you create a new grape, apply the word hello world and vine, and view, and you get the same results. It's alternative, better way of writing those sequential compositions of functions. Then the tool, and I'm not showing everything that's in the tutorial, but it's for you to explore, and has application conditions. So you can specify injectivity conditions. If you're familiar with graph transformation systems, you know about these application conditions. Can specify that the rule application should support an identification condition. Here, those are, by the way, they're visualized with some yellow condition element here in the rule. We can specify dangling condition or gluing condition here, or some custom user-defined conditions here. So this, for example, this rule would only be applicable if H and H2, these two nodes, are matched to different nodes in the graph that this rule is applied to. We also have negative application conditions. So here this modified rule world would only be applicable if there isn't already a world node that hello is connected to. So this should all be familiar to folks who have worked with graph transformation systems. Just moving forward. Okay, so here, this is interesting because it shows the filtering of identical graphs up to isomorphism. Okay, so here we have a graph that has two hello nodes, and here did I define the realm? Sorry, I just so there's a lot of scrolling here for the demo. Oh, here it is. Okay. So here we see that the normal application of this rule rel2 here, which creates a rel edge between these two hello nodes, it produces two graphs, because it can create that rel edge in either direction, but they're identical up to isomorphism, right? I mean, they're not identical when it comes to the node IDs that are shown here, but they're identical otherwise. So here, this modified, or call it filtered, application of this rel2 rule here filters out those graphs that are identical up to isomorphism. So you can only get one graph, right? Okay, so what else do I want to emphasize? Maybe so we have rules with parameters, optional nodes, and edges. I'm not going to demonstrate that because those are familiar concepts. We have graph queries. This may be interesting. I mean, ultimately, since we have graphs that are immutable, we record all the graphs and the history of graphs in the graph process. And so we have this notion of graph history in our fully persistent data structure. So here, we're in this statement here, we're creating a new graph or new grape, right? Applying the hello rule twice, the world rule, the vine rule, and then we're creating the history graph with this history command. And the history graph is just another graph. So we then view that history graph, we see a graph of graphs. That's the graph process, right? That was just computed here. So we have our first graph, that empty graph. We see here the occurrence of rule hello in step 1, another occurrence of rule hello in step 2. And then we have the occurrence of rule world. And there is 2 hello nodes now, so it can be applied in 2 matches. So we see now that graph process is forking, and we have 2 alternative graphs produced. And then the divine rule then in step 4 can be applied to either of these. You can also look at the steps. So in Clojure programs, you can view these steps applied in this graph history, and at the computation notebook, view what actually happened in each of these steps of the graph program by this built-in view steps. So we get now here a graph that shows the changes to those graphs. Here, okay, so here we see a trace for a particular graph, a derivation trace of applying hello, rule twice, world, and vine. Okay, then the next part of that tutorial talks about graph constraints. So this is ultimately just extension again of the domain-specific language for defining constraints and attaching them to graphs. So here's a very simple constraint that just says that there has to be a structure like this in the graph. So hello to grape structure, and constraints can be attached, as I said, in the GTA to graphs. So they can act as schemas. We have more complex constraints. So these we call conditional constraints here, where this constraint says, well, whenever there is a hello node in the graph, it must be connected to a grape node in the graph. Constraints can be can act as positive or negative filters. Yeah, a constraint clause can ultimately be a Boolean composite of other constraints. And by this, you can define graph schemas. As I said, you can attach schemas to graphs, right? So here, not showing this in the demo for the, in the interest of time, because I want to show you a bit more here, but you can ultimately define what's called here a schema consisting of arbitrarily many constraints, and then define graphs and attach schemas to graphs, and that is this tool's version of ultimately constraining graphs in lieu of, well, we don't have type graphs, right? But you can have these constraints, and their GrapeVine provides a list of predefined constraints, such as you have a node label constraint saying these are the allowed node labels, these are the allowed edge labels. You have roles, like you say, for example, that these are the allowed source roles for hello nodes or target nodes for hello nodes, or sorry, source roles for edges, target roles for edges. We have multiplicity predefined constraints, so you could say that the two edge can only be a too one or too many. So things that you would normally define in a type graph, we define in constraints. Attribute uniqueness, so you can have a constraint that says, for example, that a person's social insurance number must be unique. These kinds of things are covered with constraints. So then I talked about transactions and how this functional programming paradigm makes implementation of transactions quite easy. Ultimately, transactions, unsuccessful transactions can just be graph process derivation history that can just be forgotten. You can always roll back to a previous graph state because graphs are mutable and graphs are fully persistent data structures. So the way how, so in this example here, for example, we're creating a new graph, executing hello world wine, and with commit, we are, I think this is wrong. With commit, we are committing or tagging, if you will, a particular graph. We're giving it a name, and we're committing that to the graph database. So here, this result of this execution of the graph program hello world wine, we commit under the name mygraph to the database, and we can always recall that from the database under this name. And if we execute rollback, everything else is forgotten, so to say, and you can reset to an earlier graph state. So there's no complicated undo mechanism or so that we need to implement. Okay. There's a few more things that I want to point out in this demo, and then maybe we can do interaction and I can answer questions. So in the second part of the tutorial here, which I switched to now here too, there are more control structures explained here. So we have, maybe I should just. Okay. All right. So we have alternatives. So we already showed the sequential compositions of functions. So here we have the use of the alternative. So we created in this statement here a new graph. We execute the hello rule. We have an alternative between hello and world and alternative choice, and we view the result. So here the result is two graphs, right? Because after executing this first hello rule, we have graph with one hello node, and then we can either create a new hello node or attach a world node, right? So it's the alternative choice here. We have a looping control structure here. So here, this is how a control structure that executes, in this case, 10 times would look like. So we create a graph that has 10 hello nodes. So here we have our graph. We have an as long as possible control structure, which is this one here. So in this program, we create 3 hello nodes, and then as long as possible, we execute the world rule. And as could be expected, well, maybe as could not be expected, since we haven't filtered for identical graphs up to isomorphism. We actually get a whole lot of graphs that are identical. So we can use this filtered application of the world node here. Get one graph. We have a until control structure, which executes a expression, a graph program, until a particular condition is reached. So in this example here, let's say we have this condition here, constraint says, okay, if there's a hello node, it must be connected to a world node. Here's an example program. So this creates a graph with 5 hello nodes, and then executes this world rule until this condition here is met. Yeah, so we get the result here of a graph that has these 5 hello nodes, and they're all connected now with a world node. Yeah, here's the typical example that I've talked before in previous presentations about the ferryman example here. Kind of brings them together. So we have our well-known ferryman problem with the ferry, the grape, the goat, and the wolf on one river side. We have 2 rules: ferry one thing over to the other side and cross empty. And we have our constraints. One thing can eat another thing, which is a parameterized constraint, and a constraint that allows us to find out whether we've done everything all on the other side. And in this functional program notation, this will be the program that solves the ferryman problem here. We have the setup of the situation, and then until everything's on the other side, it either ferries over one item or crosses empty, and it makes sure this is a negative application of these conditions, that the wolf cannot eat the goat and the goat cannot eat the grape. Then this program executes, creates this graph as an output, and we could see here everything's on the other side. Right? And we can look at the history with the history graph, what actually happened in this execution. Trace again the graphs that were created here from the initial empty graph, setting up the initial state, and then the unsuccessful explorations of the graph program, and the successful exploration ultimately up to down here. And as we saw earlier, we can look at the steps, the actions, the changes that the graph program did in the graph history in more detail. So this was the original setup of the problem: ferry one over, crossing empty, ferry one over here. This is the grape. Ferry one over, cross empty, and ferry one over until the solution is reached. Okay, so this problem can also be solved alternatively just by attaching schema constraints. So we could just have a schema that only allows safe moves. That's just an alternative way of writing that program. And maybe the last thing that I want to point out, well, maybe there are two more things that I want to point out. One that we've recently done as an extension to the tool is parallel rule applications. And the application that the tutorial here talks about is one of the tool benchmark studies at the ACTAFT 2007 tool contest here, which is the Sierpinski triangles. For some of you who maybe remember others, this is described in the tutorial. If you open this up, Sierpinski triangle is a kind of a fractal approximation of a structure here, where each triangle ultimately is replaced by 3 more triangles where the inner area is dead. A tool like GrapeVine that allows ultimately all of these execution matches to be performed in parallel as parallel graphs that are produced, also would allow you to potentially merge these computations again if they are parallelizable. So that's a recent extension that we made to the tool to check whether they are mergeable and then to merge those again. So here's the way how a step is defined in GrapeVine. So we're looking for a triangle that has these 3 corners, like the top and the left and the right, and we're creating 2 more triangles. And you can see here that so the parallel rule application, the syntax for the parallel rule application is adding an asterisk to the rule call here. So when we apply this for the first setup, there's the starting situation that it just has 1 triangle. This is the output, right? That's predictable. I mean, there's just 1 match possible, so it's just 1 graph. So this is now a new graph called generation 1, gen 1. Now we're applying this step rule again on the generation 1 graph, and we see here there's 3 alternative matches, right? 3 graphs are produced. I can zoom a bit like this. Okay. Now it becomes probably a bit hard to read, but at least it's all on on the screen. So now let's see the impact of the parallel rule application here. So you have this 1 graph. And release. For some reason, it doesn't allow me to zoom. But this 1 graph and where everything's merged, right? And this computation here. So then we can apply the step again on this generation 2, and we get again just 1 graph. And now it becomes really, I mean, the layout is really bad right now. You probably can't see this anymore, but at least you see that this is 1 graph, right? Because it merged those parallel computations. And then we can use our looping construct here to say, well, let's generate generation 7, for example, right? And makes a very easy implementation of this Sierpinski. I don't know why I have to delete all here, but this Sierpinski problem. This rendering here is probably creating some problem with the graph-based engine, maybe because the graph is too large. I'm not sure. I didn't actually try this. This may be the part where the demo crashes, because this graph is really large, right? I shouldn't have done that potentially. Okay, let's see. Maybe it comes back at some point in time, but it'll create probably quite a bit of work for this graph-based engine. We'll see. Okay. Bottom line is though, so here we're using actually some data. We did some timing here. I did some timing about how performant this approach is for computing higher generations of the Sierpinski triangle. And I think on this machine, these are some of the, okay, I can't show this right now because the system is still busy with this. Okay, I did make some comparison in terms of how fast this is compared to some of these other performance results that were published at this time for this tool contest. And while it is kind of on the slower side of things, because ultimately it's a database underneath, it's not that bad in terms of the complexity increase. It's not bad. And when it comes to just scalability on the size of the graph, there is really no limitation other than what the Neo4j database can do. Performance-wise, it's not bad. I had this graphed out here. The computation notebook allows you to do list plots and all of these things, but right now I think we're stuck. I shouldn't have tried to put this on the screen, this graph here. So maybe this is the time when the demo crashes, and I may go back to the slide deck. Okay. This is just to show that you don't have to use a computational notebook, but the IDE. So let me just wrap up then. Okay, so we found that since we do these applications in the computational notebook, in particular in a functional manner, it's much more convenient because you can have these cells. They're idempotent. They're not dependent necessarily on the order of execution of things. A graph that has been computed and named as, for example, whatever, graph 7 will always be the graph 7. It will always have that state, and you can compute other things from it, but you can always execute the action on graph 7 again. You get always the same result. It's the implementation of the engine is much easier because I don't have to worry about reconstructing graphs anymore, backtracking. All of this engine in the older version of Grape, that was quite complicated implementation. The graph transformation algebra, the GGA, is the foundation for this, as I showed here, and the tool implementation shows that it, at least for the problems that we're looking at, can implement this with reasonable efficiency and performance. Our current work is really on just exploring more benchmark problems, more applications, showing with case studies that this is a feasible approach, because I know there's some concerns about whether this actually is useful and feasible for larger scale applications. So that's what we're currently working on. So that's pretty much what I had here. There is this GitHub link here. It should be a one command to get the Docker app. You may have to download then. I mean, the Docker command will just download the Neo4j and the Grape Docker, then you can play with it. The tutorial is built in, right? If you have any difficulties or questions, here's my email address, and I'm happy to respond to these and look at your maybe error reports on GitHub. Thank you.
Okay, thank you very much, Jens. I think Steffen had a couple of questions, which I just ignored during the talk, because they're sort of more general. But Steffen, do you want to go ahead and ask them directly?
Sure. Thanks. I mean, these are perhaps sort of less questions about the sort of formal algebraic side of things, but more in the implementation, right? So it's fundamentally you're creating loads and loads of graphs, which are potentially large graphs. I mean, in your examples, perhaps less so, but in principle. And so I was wondering how or if you have any mechanisms for managing those graphs efficiently and the memory that they occupy, especially given that there are sort of typically just small changes between them, right? So are you actually copying the full graph, or what are you doing? These sort of things I was interested in. And the other question I had was I like that you're talking about this as a functional approach, but then there are little things like you've got to have, if I understand correctly, globally unique commit labels, or sometimes you have these issues where sort of it was still thinking that there should be a particular constraint label there which it couldn't find, or things like that. So is there, because of the database underneath, is there still something that fundamentally tracks some sort of state around, or am I misunderstanding something there?
Okay, so yeah, I think I'll respond to these two questions in order. So yes, there is quite a bit of sharing between the different graphs. There is this paper on this fully persistent data structure. I think it is the ICGT 21 paper or so, which we can put on there. But ultimately, small changes, if you produce another graph that just has a small incremental change from a previous graph, they share 99.9% of the storage structure. So it's just an incremental change that's recorded, and it's taken quite a bit of thinking and putting that data structure together and making that efficient. But it's not that graphs are completely copied. I mean, this is based on ideas of ultimately fully persistent data structure in functional programming. There is a lot of sharing that goes on underneath. So that's there is a paper on that if you're interested in that topic, which I can share. So you talked about tags. So there was this one time in the demo where it talked about committing graphs to the database by means of tagging it with a label or something like that, right? Maybe that's what you're referring to. Ultimately, all the graphs, when they are created, they get a unique ID, and you can recall them by that unique ID, right? So you don't have to tag them. Just this unique ID is just very cumbersome to handle, right? So you may just want to give your graph that you care about a user-defined name committed under this, if you will, name, and then, yeah, of course, that name then needs to be unique. It's a key, right? You can look it up like that again. Then there's also, of course, the names for things such as rules and constraints. These also need to be unique. I mean, you define them under those names, and they are then unique. What I would like to do in the future in terms of this notion of complete history of a graph transformation systems is also to version rules and constraints, so that you have a full history of what went on in the system, some kind of similar like a versioning system or so. And but we don't have that yet. The rules and the constraints, they are not versions. Once you change them, they're changed, right? So that when you have a history graph that says, okay, rule hello was executed at this point, and then later on, that rule may be completely different when you have redefined it, and there's no way to tell right now in the system. But that's something to work on in the future. Does that answer the second part of the question, or did you have a
sort of? I guess I was wondering if I so the graphs and everything that happens to the graphs, right? And all of that's managed functionally. So I've got to sort of basically just pass around those references to the graphs, etc. Right? And so I create a new grape, and I apply stuff to it, and I do stuff with it, and within the context of that sort of invocation chain, all of that is just sort of local information and so on. But then, say somewhere in there, I create a commit. Now I can see how I can track that label around within that sequence of calls, or that chain of calls, and so make sure it's unique. But now, say a little further down in my program somewhere else, I create a separate grape, and I do a sort of chain of invocations on that, and within there I create another commit. Now somehow it feels to me, and maybe I'm wrong, but somehow it feels to me like at that point the stateless, stateful kind of differentiation breaks a little bit, because I'm feeling, I believe I'm programming in a stateless functional manner, but actually I've kind of got to be aware that I've created a commit somewhere else in the program, or possibly even in a previous run of the program. I don't quite know how you manage the database to ensure that I'm not duplicating things like tags here. Is that, did you understand that correctly, or am I missing
totally
something?
yeah no, you're totally right. I mean, ultimately, as soon as you say, okay, now I'm giving this graph a label, like my favorite graph, right? Then this, if you will, index structure that lists all these different labels that you have given out, that becomes a side effect for computation. It becomes kind of a global variable. And if you somewhere else in the notebook you want to also call a graph my favorite graph, it says no, that graph's already that label's already given, so that those code cells will no longer be idempotent. They will just, there's this global singleton of labels that you've given to graphs, and that is absolutely, that's the nature of the beast. I don't know how to do it differently.
No, fair enough. It wasn't meant as a critique. I was just trying to understand,
right,
to see whether I've understood correctly what you were saying.
Yeah, you're right. This is not fully functional anymore. No.
Okay. Yeah. No. Thanks.
Okay. Detlef had a question.
Me, I have my hand up.
Yeah, I said Detlef.
Okay, so just on this term functional versus non-functional, I didn't quite get where you make the distinction, or let's say between, and maybe that's different for you, deterministic and non-deterministic. I mean, I think you stress in your talk yourself, to get this kind of functional or deterministic input-output semantics, you do need to consider the set of all outputs, and only then it will be, because you do have matches, you have different rules you can choose, otherwise there's no way you have a functional behavior. So if that is functional, this view, I look at the set of all possible outputs, I think then I think almost any graph transformation language I can think of would be functional, including GP2, I would say. So to me, it appears the distinctive feature is more this, what you just discussed, this feature that you can name graphs and pass these graphs around in programs, and so graphs as, I don't know, first-class citizens or so, but not deterministic versus non-deterministic. That's my feeling.
Yeah. So this maybe, you're right. I mean, this maybe comes really from somewhat of a practical view of things. Right? I like to solve kind of real world problems with graph programs, and use them for, well, software engineering applications. And what in these other systems that I've used before, when I call a rule or I call a graph program, it usually it's not. I mean, I call it as a subroutine, as a function, if you will. But what I get out, first of all, is I guess a mutated graph. So it's not really like that. You could say that there's an output graph, but it's not. It's the mutated graph, and it's not a function. I'm calling it as a function, but it just gives me a result, right? And of course, if you have a backtracking system and you don't like the result, then potentially you may ask for another result or for a different one or something like that, and just give me something else, right? But it's not in this notion of an input output, like a box that has an input and an output. It's not a function in that sense, right? So
yeah, that's why I wondered what your view of function, what the characteristic feature of functional versus non-functional is in your view.
Well, I mean, in my view, it's the characteristic of a mathematical function where the output is determined by the input, right? It's a functional.
Yeah, but I thought we agree that to have a function there, you need to consider all possible results and lump them together in a set. Or
yes, so that's why that's, I mean, there's no magic here, right? That's why I made this, if you will, some sort of a cheating trick, or almost like to say, okay, it's only functional because I'm lifting two sets of graphs, right?
Yeah, but I mean,
so now it's.
What I said, try to, in my view, you could do that with any language, and then you get this kind of. So I just wonder if functional versus non-functional is the distinctive feature of your language.
Right.
It appears in this graphs as first-class citizen, which you can move around and give names and so on. That's my feeling. Is more the distinctive thing. But okay, that's just a comment.
Yeah.
Heiko wants to say.
Just to say, so I think there are probably two dichotomies here, and maybe we get mixed up between them. So there's one which is functional versus relational, and the other one is functional, as in when you talk about functional programming, maybe functional versus imperative, or functional versus, I don't know, object-oriented or something like that, although there's probably no conflict between object-oriented and functional in the user.
Yeah, but then my question is, what are the genuine functional properties? Because naming an object, I can also do in an imperative language, can't I?
No, I'm just saying, so maybe this is functional versus relational rather than functional versus imperative, or maybe it's both to some extent. But
functional versus relational, this is again the thing with deterministic versus non-deterministic.
Yeah, exactly.
Okay.
But I think it's both in a sense, because there is a functional language underneath it, isn't it, Jens? So there is no. Yeah. You can think of it in both ways, I guess. Right, Nick?
Thanks, Jens. Very interesting talk. I just wanted to briefly mention that we had on YouTube a question. Unfortunately, on YouTube, you don't see the real names of people, but somebody asked if you might have a research internship opportunity for that kind of project.
Sure. You gotta know Clojure. And those students are hard to find, but if you're a Clojure programmer, contact me.
Okay, so whoever is still in YouTube might see this. You see the email address on the screen, and you can get in contact yourself. Maybe I missed that part. Is the kind of conditions you can specify? I imagine that is the usual calculus of nested conditions in principle, if on ones, or is it one level of conditions?
And no, it's nested. Yeah.
Okay. Good.
So arbitrary. Yeah. Nested conditions. Absolutely. Yes.
And I was just curious, like in your practical applications, so I guess the conditions or constraints could get quite complex. Do you have some experience on performance of your code? I mean, is it something that is usable, or is it more of a prototype for the moment?
So we're working on ultimately benchmark studies. The Sierpinski example, for example, really extends to really large graphs. Again, while the performance of the code, maybe partially because everything's kind of in the database, and there's a client server communication between the Clojure runtime and the Neo4j database. It's slower than, for example, I mean, you know, I think GP2 would probably just browse by, right? Or other languages, but it's not bad. I'd say I want to publish about this, but this is still these benchmarks I'm still producing. Certainly, I think when it comes to performance, the overhead of a system like that is more than if you just have something like a main memory in process computation. But then again, the scalability in terms of the sheer size of graphs that you can produce, I think is an advantage of this approach, right? And the fact that the Neo4j database can you know, have graphs that are potentially much larger than what you normally fit in the main memory, and the fact that you have persistence there, where you know, you can pick up your graph states again at any time without having to recompute in memory state again.
And
but yeah, so I mean, this is a bit wavy answer. So, but I'm working on the benchmarking at this point. Yeah.
Right. And the other question was, because you already have this history graph, I think you called it. Do you have anything implemented to do some static, some for example, concurrency analysis on this graph? And can you sort of see pieces? I think one time I saw a talk by you where you could do some analysis of dependencies between steps and stuff like that, but I'm not sure if it's in this program. Is there some?
So there's early work in this. So this is part of, for example, this parallel rule application, the parallelizable rule application. Like we saw that. Unfortunately, I can't really see if my graph is terminated here. No, it's this. I made this mess here. It's a graphist problem. I've seen. Fell into this trap before. So there is, when you do this parallel rule application, there is some dependency analysis, and it only produces the merged graph if the rule applications are parallelly independent. But that's only for right now implemented only for a single parallel step.
Okay.
Right. So it's not for an entire kind of graph computational unit for an entire block. But we're working on that. Yeah.
And last question. I mean, do you have primitives to play with? Like, for example, do you have? I mean, if you have, I guess, double push-out rewriting, do you also have push-outs available as a primitive one can use? Or, I mean, could one stitch together one's own rewriting algorithm, or is it really tailor-made for, say, I don't know, single push-out CESCI or something else?
No, we currently don't have the primitives available.
Okay,
but that would be a good direction for the research.
I'm asking only because there is currently this one interesting alternative project, this algebraic rewriting.jl and Julia. I was just curious to compare the two, where the one in algebraic rewriting is more category theoretically motivated, maybe. So, yeah. Okay. No, but they're very interesting. Thanks a lot.
Yeah. Welcome.
Okay. Any other questions? Otherwise, I would suggest that we close the official part of the seminar and then maybe stay around and have a friendly chat afterwards. But yeah, so if there's nothing else that we want to discuss in public, let's say, then thank you again, Jens. And yeah, we see each other, I guess, in a couple of weeks again. Nick, do you have the title available for next talk?
Yes, so next week we have something slightly, next week in 2 weeks on October 6th, we have Ryan Wisniewski, I hope I pronounced it correctly, who will tell us about functorial data migration, so something slightly different, more database related. but perhaps also interesting to this community. And yeah, also thanks from my side to you, Jens, and to Raiko and everyone who attended. And I will now close the YouTube live stream. If you are still on YouTube, you want to chat with us, we might stay around for a bit. Yes, and you will find the link to register in the YouTube chat. So thanks, everyone.